exploring the science behind blue skies and red sunsets. Every kid has asked us a question that usually sounds like the following: why is the water in the sea blue? But as soon as I touch it, it becomes transparent. And our answer would be, because the sea is only reflecting the color of the sky, which is blue. But water doesn't have a color. And if we are unlucky, the kid then asks, okay, then why is the sky blue? And somehow it seems like a hard question to answer. Don't worry, you've come to the right place to be able to understand why, in fact, the sky appears to be blue and why it changes color depending on where the sun is located in the sky. Through this video, you will explore the scientific answers to these questions and find out why our sky and sunsets appear with such vibrant colors. Dive into the world of light, matter, and atmosphere, and learn the reason behind the mesmerizing blues and reds of the sky. Keep watching to never hesitate ever again when a child asks you this question. The sky is one of the most mysterious and captivating things in our environment. It's constantly changing and always fascinating to look at. First of all, it is important to understand that the sky is not blue because of a pigment. The universe and the night sky are essentially black due to the absence of light. Where there are no stars to emit light, there is no visible light, and therefore it is black. The air is not blue either. Air and gaseous oxygen are both transparent, allowing visible light to pass through. Therefore, the origin of the blue sky and color is not pigmentary but structural. The process that creates it is purely physical. It is an action of matter on light, and this is what allows to act on specific colors even without pigments being involved. In the case of the sky, the colors making up white light are refracted. It is also said to be diffused. This phenomenon is called something known as the Rayleigh scattering, which is when molecules and particles in the atmosphere break up visible light into its component colors. First, it's important to understand the basics of light and what happens when light passes through the atmosphere. White light consists of all the colors of the visible spectrum: red, orange, yellow, green, blue, and purple. But when light passes through our atmosphere, the molecules and particles in the air break it up into different colors. When the sun is high in the sky, most of the blue light gets scattered throughout the atmosphere. The Rayleigh scattering causes blue light to be scattered much more than other colors, so this is why the midday sky looks blue. But then why does the sky appear blue and not violet? Wouldn't it make more sense, knowing that the Rayleigh scattering disperses more the shorter wavelengths are, that the sky appears to be violet? Well, in fact, violet is scattered even more than blue. The trick here is that although violet is indeed part of the solar spectrum, our star emits much less violet than blue. These are very short wavelengths and are not very present in sunlight. In fact, the peak in the spectrum, that is the most emitted wavelength in the solar spectrum, is green. So there is more green than blue than violet, and even red or orange. We don't see it though, as the mix we perceive is mostly white or yellow at the ground level. If the sun was much hotter to the point of emitting more violet than blue, the sky would appear to be something like a bluish purple. Moreover, ultraviolet, whose wavelength is even shorter, is so much dispersed that UV camera images are naturally blurred because of it, even for a landscape not too far away. Does that explain why we see the sun as yellow when in fact it emits white light? Yes, it is explained by the fact that the sun is very, very far away from us. It is like a big glowing ball of light in the sky. When we look up at it from the ground, it looks yellow. That is because of the air in the sky. It filters out some of the colors, so we only see yellow. It's like a fun little coloring game. We have white minus blue, which gives us red plus yellow plus green. And I presume you all know your additive colors. Red and green make yellow. Overall, we obtain the color yellow seen from the ground. But if you look at pictures taken from space, you can see that the sun is really white. The sun is actually referred to as a yellow dwarf star, which is a term used to describe its size. However, even though it is classified as a yellow dwarf star, it is not because of its color. The term yellow dwarf simply indicates that the sun is of a certain size, which is typical for stars in this classification. The lower the sun is in the sky, the more atmosphere its light has to travel through before reaching our eyes. This means that more of the blue light will be scattered away, leaving primarily the reddish component of white sunlight to travel directly to our eyes. As a result, the setting sun will look red. This is because the shorter wavelength blue light interacts more with the small molecules, causing it to be bounced away from the original sunlight path. Thus, less blue light reaches our eyes, resulting in the red hue of the sunset. This phenomenon is naturally more noticeable in places with less air pollution and in areas that are farther away from cities, as large amounts of airborne dust and particulates can block the red light from reaching our eyes. Additionally, dust and debris in the atmosphere can cause the sun to look orange or even purple when it is low in the sky. This occurs because dust and particulates scatter different intensities of light at different angles, causing some regions of the sun to appear brighter than others. As the sun sets, the sky turns darker and darker until it eventually becomes black. The setting of the sun marks the end of the day and the beginning of the night. As the sun slowly sets, the sky gradually turns from a deep blue to a dark, star-studded black. Watching the sunset is a beautiful and calming experience, one that can make anyone feel at peace with the world. To add to this, what's really fascinating is that the same effect that causes the sky to appear blue and sunsets to be red can also be seen in other parts of the world. For example, if you look at the sky in Antarctica in the middle of summer, the sky appears a brilliant green color due to the increased number of ozone particles in the atmosphere. This is because when the sun is lower in the sky in the polar regions, the light is reflecting off the particles in the atmosphere in a way that makes the sky look green. There's also another reason for a green sky to appear, taking for example what's been happening in South Dakota. I'm sure you've seen it on social media. Residents of Sioux Falls, South Dakota witnessed an unusual phenomenon on Tuesday night as a derecho storm brought powerful winds and a green sky. The green hue was caused by severe thunderstorms with a lot of water content that scattered blue light combined with red and yellow light from a sunset. Social media users posted images of the strange sky, and the Department of Transportation traffic cameras also captured it. Meteorologists explained that the green sky can be indicative of large hail. If you haven't seen all the cool pictures capturing the green sky, don't hesitate to take a look. What would the sky look like in different worlds with different atmospheres? Let's take a look at the moon, our favorite neighbor. The moon does not have an atmosphere. No light from the sun is being scattered by the molecules making up the atmosphere. Therefore, there is no specific color for a sunset on the moon. Before we continue with the sun and Mars, stay tuned afterwards if you'd like to watch our earlier release on why is it so difficult to return to the moon if we have done it before. The sun will look white all throughout its trajectory in the sky of the moon. An interesting comparison would be considering the Martian sky. The sky on Mars looks very strange compared to the sky we see here on Earth. The sky near the sun looks blue and the sky far away from the sun looks red. That's because there is a lot of special dust in the air on Mars. This dust scatters the sunlight, so it looks blue near the sun and red far away. When the sun sets on Mars, it looks extra blue and beautiful because of the dust. But even more interesting is the night sky on Mars. We can often see celestial objects that are too dim to be seen on Earth without a telescope. Mars has no bright moon like Earth, so the stars shine very brightly in the night sky. When you look up on a Martian night, you can see constellations of stars, galaxies, and even distant planets. It's a view that is truly breathtaking and awe-inspiring, but that's for another video. This universe is a fascinating one. You start with one simple question like why the sky is blue on Earth and find yourself diverging talking about the night sky on Mars. Why is it so difficult to return to the moon if we have done it before? The last time a human was on the moon was in 1972. Since then, technology has taken giant steps and more countries have developed their space program. But despite this, human beings have not returned to visit the moon. What are the reasons? Let's find out. The main motivation. To find the reasons that led to the trip to the moon, we have to go back to the end of the decade of the 60s.
After World War II, during the Cold War, the United States and the Soviet Union engaged in the space race, a stubborn struggle between the two powers whose ultimate goal was to place a citizen of the nation on the surface of the moon. From this struggle, in which both nations intended to demonstrate their military and technological superiority over the adversary, the United States would emerge as the winner. The trip to the moon, more than an end in itself, was a way to show the world who would set the pace of the international political agenda for the remainder of the century. Reaching the moon had more of a political purpose than a scientific one. In a different historical context, out of simple scientific concern, would we have reached the moon in 1969? Everything seems to indicate that it does not. As we have said, the motivation for the Americans to send a human crewed mission to our satellite was the tension generated by the political situation. Without this rivalry with the USSR, it would have been hard to imagine that the American government would mobilize the nearly 400,000 people who participated in the Apollo program and dedicated to it during the 14 years that it lasted, the equivalent today of about $120 billion. Today, it is unimaginable that the U.S. government would again fund a trip of this nature at such high cost to the nation. The high cost of stepping on the moon again. Reaching the moon was not an easy feat to achieve because, in addition to the technological challenges we will discuss later, there were also many economic challenges. A law signed in March of 2017 by President Donald Trump gave NASA an annual budget of around $19.5 billion and stands at nearly $20 billion today. But although this sounds like an astronomical figure, in reality it is not if you consider that the total is divided between all the divisions of the agency and all the ambitious projects like the James Webb Space Telescope, the giant rocket project called the Space Launch System, and remote missions to the Sun, Jupiter, Mars, the asteroid belt, the Kuiper belt, and the edge of the solar system. In addition, NASA's budget is somewhat small relative to its past. Since 1960, the economic allocation dedicated to the American space program skyrocketed, reaching the record figure of 5.3% of the national budget in 1965. But 5 years later, in the early 70s, and resolved the space race in favor of the Americans, NASA suffered a significant budget cut for various reasons, including the loss of political interest in the moon and the accident the Apollo 13 mission suffered. These events would lead to the cancellation of the Apollo 18, 19, and 20 missions, making Apollo 17 the last human crewed mission to the moon. As a result, for the last 40 years, NASA's budget has remained below 1%, and for the last 15 years, it has been heading towards 0.4% of the federal budget. In other words, if today we have not returned to the moon, it is, on the one hand, a lack of interest on the part of the government, and secondly, a lack of economic resources. What happened to technology? Today, NASA has the new rocket SLS Space Launch System, which will be the successor of the Atlas V that was responsible for taking astronauts to the moon. This rocket made its debut with the launch of the Artemis 1 mission, which was a success, managing to take the Orion capsule to the orbit of the moon, which will be the new spacecraft that will transport humans to the lunar surface. Something that has caught the attention of many is that before the launch of the Artemis 1 mission, it was canceled 2 times due to failures in the rocket's fuel chambers of the rocket, and therefore it was necessary to perform more tests before the ship could be launched. But why was it so difficult to launch the SLS? Isn't NASA supposed to have years of experience already? The reality is that the launches of the Apollo missions were not easy either. As you will remember, the mission that managed to land successfully was the 11th. That is to say, before the 11, 10 missions did not get it for various reasons. Most of them had several cancellations, either due to weather problems or technical problems. Some Apollo missions didn't even get off the ground, but it's hardly talked about. It's also worth remembering that during the space shuttles, NASA had many problems getting them off the ground, though they already had the experience of the Apollo spacecraft. The most common problems during shuttle launches were almost always in fueling systems, since this was not the same as that of the Saturn V rockets and Apollo spacecraft. The shuttles were extremely complex craft that mixed a rocket's power with an airplane's aerodynamics and had engines that used solid and liquid fuel. This complexity was what caused technical failures in all launch attempts. In fact, according to the Registry of Launch Cancellations, shuttle launches are the ones that suffered the most cancellations. Some were canceled up to 5 times before taking off successfully. The problem of fuel supply. Before successfully taking off, the Artemis 1 mission was canceled 2 times due to technical failures in the fuel system. These failures are the same ones that caused the cancellation of the Apollo missions and the same ones suffered by the shuttles. Fuel leaks are the most common failure in rockets, and one of the main reasons for takeoff cancellations for more than 50 years. But why does this problem still exist today? The fault lies with the fuel used by the rockets, hydrogen. This is the simplest and lightest element of all. On Earth, it exists in abundance, but it is mixed with other elements, and molecular separation processes such as electrolysis must be used to obtain pure hydrogen. Hydrogen is a highly light element, so much so that putting together a single gram of material requires billions of hydrogen atoms. Hydrogen is so light that it can sneak through any opening, however tiny it may be. In a typical environment and average temperatures, this is not usually a problem, but leaks are much easier to occur in a cold environment and high pressures. It is precisely these environments in which space rockets operate. For rockets' fuel tanks to remain full of fuel, they must be permanently connected to terrestrial cooling systems by cables and hoses until the moment of launch. At the time of takeoff, some connections separate from the bridge. It is right here where leaks usually occur, since these connections cannot be screwed tightly, and it is tough to avoid leaks when they are at high pressures and shallow temperatures. In short, it's hard for rockets to take off because hydrogen is used as fuel. But if this is the problem, why not use another fuel? Reusing rockets. The reason why NASA continues to use hydrogen fuel is its high efficiency, since it is the element that provides greater thrust and less weight. Still, another important reason is the law. We're not talking about physical laws, but political ones. In 2010, the U.S. Congress ordered that NASA would have to continue using the rockets that were used in the shuttles as part of the SLS rocket program. In fact, you may not know it, but the SLS engines are the same as those used by the space shuttles at the time. As the budget was cut, Congress suggested that to optimize resources, NASA would have to use the contracts, investments, budget, workforce, industrial base, and existing infrastructure in the U.S. that were used for the space shuttle in the new SLS program. Likewise, would also be reused the Orion 1 and the existing propulsion systems, such as the liquid fuel engines that cause so many leaks. The external storage tank and the solid fuel engines would also be reused. All this was reused and conditioned to the new Artemis 1 project. In other words, the Artemis project, which seeks to take new astronauts to the moon, uses the same technology, rockets, engines, and launch base that space shuttles used more than a decade ago. That's why getting back to the moon is so tricky. Beyond touchscreens, the technology of the Artemis 1 program is not so different from what we had 50 years ago. Moreover, perhaps the most potent reason we haven't returned to the moon is the simplest of all. There hasn't been a need to go back. The missions of the Apollo program were so prolific that apart from the countless experiments carried out on the moon, so many samples of lunar material were collected that, even today, many of them remain unstudied by scientists. To all this, we must add that in the coming years, NASA's interests will focus on objectives such as Skylab, the laboratory in Earth orbit, or sending probes and satellites to many other corners of the solar system. And perhaps the question is, why should we return to the moon when there is so much still to be explored on the rest of the planets? In light of recent scientific advances, there is nothing to criticize NASA for. Today we explore Mars with robots, discover new solar systems almost daily, and detect phenomena such as gravitational waves that until very recently were only part of the theory. As we have seen, there are several reasons why we have not been to the moon since 1972, and yet none has to do, for example, with the strange conspiracy theories circulating for several years on social networks. Just because we haven't come back doesn't mean we won't. The horizon of the next human crewed mission to our satellite will be marked by NASA's Artemis project that aims to put a man back on the moon. And it may also be that on this occasion, imitating Neil Armstrong in 1969, is a woman who takes a new step on the surface of our natural satellite.